All right, an application of what we have learned for the pressure variation of fluid, there is something called Pascal's Principle or the hydraulic lift. So let's see how it works. So hydraulic lift. If you went to a service station to get your car fixed or checked, probably have seen somebody lift your car. How does it work? At least what's the principle behind it? Well, let's see. You would have, let's consider the following thing here. You have a fluid, it's incompressible. You have a section here and a section here. Right? There is fluid inside. And we would have a piston on this side here. The piston is there to ensure that the fluid doesn't flow either way, on either side. And then there will be another piston here, and it's larger. This piston would have a larger area. So this one here is area 2, and this one here has area, cross-sectional area 1. And so they're just sitting there. Imagine the pistons are weightless. And so the fluid here and the fluid here, they will be at the same level. Now, if you now place a car in here, let's see, you place your car and you raise it, right? For example, if you put the jack, do this, you raise the car. And so what happens? Well, if you raise the car will be here, will displace, will come here, and we would like it to be in equilibrium. The car will be here. And so somebody has to push this, so the fluid here will go up, and here it will come down. So the fluid will come down here. I'm exaggerating, it's not to scale. So the pistons are like this. So maybe I should make another drawing. So let me make another drawing just to get the point. Okay. This piston is here, and this one is here. Yeah, and there is a car here now. There's a car there. And here, I mean, the car doesn't just rise by itself. Somebody has to push it from here with some force here. Let's call it F1. With some force F1. So this is fluid in equilibrium. If you're at this point here, let's calculate the pressure here, and then we'll calculate the pressure here and see what happens. Let me call it here the pressure on the left, and here it will be the pressure on the right. And they have to be equal. Remember, you have a cylinder. If the pressure is not the same, the fluid has to move, and the fluid is in equilibrium. It has moved a little bit, but once you stop lifting it, it will just be there. I'm just asking, how much force do I need to hold this fluid up there? This is H. So this is H from the left, and this is H from the right. Let's calculate the pressure on the left, the pressure on the right, and then we'll set them equal, because at the same level, it has to be the same pressure. So the pressure on the left will be, well, you will have atmospheric pressure plus the pressure due to the force, and pressure due to the force will be force divided by area 1. So you will have P atmospheric plus the F1 divided by area 1. In addition to that, you would have rho GH, this plus the density of the fluid times gravity times the depth, plus rho G, the height, the depth on the left. All right? Okay. And then the pressure on the right side will be, you start at atmospheric pressure, and then you place the car here. And the car here will have a force F1, let's call it F2 divided by area 2. That's the pressure due to that force, F2 divided by area 2, plus rho g, and then the depth from the right-hand side, the depth from here all the way to here. Now these two are equal, again, because two points here, if they don't have the same pressure, then you can imagine a virtual cylinder here, horizontal. There will be a net force either from the left or from the right, and the fluid has to displace. And it has to displace until it comes to equilibrium. We are in equilibrium right now. Okay. So we'll set them equal. Pressure from the left will equal to the pressure from the right. Let's see what the consequence is. Pressure from the left is P atmospheric plus F1 over A1, and then plus rho G H from the left equals this. P atmospheric plus F2 over area 2 rho G H from the right. Notice the atmospheric pressure simply cancels. I mean, it's on both sides. It just adds up on both sides, so it cancels. And so here we have, let me solve for this. I will take this to the other side, so I get the force F1 over area 1 will equal to F2 over area 2 plus rho G, and then the height from the right minus the height from the left. Height from the right minus the height from the left, this minus this will equal to this. And I'm going to call this H here, so just H. So you have, let me write it in blue first, or yeah, in this one. F1 over A1 is equal to F2 over area 2 plus rho G H. Let me do this. Now, if they are at the same level, let me make it bigger here. If they happen to be at the same level, here is a car, and how much force should you push from here? F2. If they happen to be at the same level, then H is 0. There is no difference in height. And in that case, F1 over A1 will equal to F2 over A2. Okay? And F1 will be much smaller. So let me just emphasize. Let me write that. Let me come to the whiteboard and draw something. So if they are at the same height, just to hold it in place, how much force do I need? They are at the same height. And so you have the car here. The weight of the car would be F2. And this is area 2. And this is F1. How much force do you need to push with to keep the car at the same level? You get a car here. Or some weight. And this here is area 1. Well, again, if there is no difference in height, this is 0, and you just have F1 over area 1 will equal to F2 over area 2. So you have, let me write here, F1 will equal to area 1 divided by area 2 times F2, okay, times F2. So for instance, let's say the car is 1,000 kilograms, let's say, e.g. example here. If the mass of the car is 1,000 kilograms, then F2 will be just the weight of the car, that's 9,800 newtons. And let's say the side where you put the car has a diameter of, let's say this one here has a radius of, let's say, 10 centimeters. R2 is 10 centimeters. And then here, the radius will be typically smaller. Let's say R1 will equal to, let's say, 1 centimeter, all right? 1 centimeter versus 10 centimeters. what would be the relationship? Well, then F1 will equal to area 1, which is pi r1 squared, divided by area 2, which is pi r2 squared, times F2, which is 9,800 newtons. And so this cancels, and so F1 will be R1 over R2, the whole thing squared, times 9,800. And so R1 over R2, you will have 1 over 10, and you square it. I don't need to convert to meters because centimeter over centimeter cancels anyways. Times 9,800, and this gives 98 newtons. 98 newtons. And 98 newtons corresponds to about 10 kilograms. So to lift a 1,000 kilogram car, you need to put about 10 kilograms of weight here, which is about 22 pounds. You put 22 pounds here to balance 2,200 pounds. So it's a huge leverage. But you're not getting something for nothing. It's really not very different from having, let's say, a really heavy object here and making a really long lever here and only putting a tiny object to balance a very large object. The reason is, see, when you, for example, when this piston drops, let's say, by 10 centimeters, this one only rises by, if this one drops by 100 centimeters, that one rises only by 1 centimeter. Why? Because the fluid that you displace here, it has to move to the other side. But, so this volume of fluid that you moved from here, it has to come to the other side. But the volume here, because the area is 100 times larger, the height would just be 100. So you're not getting something for nothing, but it's still a good piece of technology, obviously, because you're able to lift really big object instead of taking the car apart and then lifting it piece by piece. That's essentially what you're doing. You're lifting it one increment at a time without disassembling the car. So let me show you an example of this one here, where there is a difference in height. So for example, let's say I have this. The diameter of this area here is 6 centimeters. The diameter here is 25 centimeters. The height difference is 2 meters. And the mass of the car is 1,300 kilograms. So you go to a service station, you lift here by 2 meters. And the question is, how much force is needed here? How much force is needed there? Our friend is here, this one. Okay? And again, I want you to appreciate that everything we got is Newton's law, nothing more. So we will say F1 over area 1 will equal to F2 divided by area 2 plus rho G H. And actually the fluid here, I think it's oil, and it's, let me just write it down. It's 900 kilograms cubic meters. So let's say the fluid that's here is oil, some kind of oil. It's 900. I quoted the number, but I forgot. My memory is pretty short. So 900 kilograms per cubic meter. Okay, so we're going to use this. So we will say we want F1, so I'm going to multiply both sides by area 1. So F1, actually before I do that, let's multiply everything by area 1. So I got area 1 over area 2 times F2 plus rho G H times area 1. So F1, so the question is, how much force do I have to apply here to lift this car and keep it at that height? Area 1 over area 2, that's pi r1 squared, but r1 is diameter 1 over 2. So remember, radius is diameter over 2. And then the same thing here. Area 2 is pi, diameter 2 divided by 2, and don't forget to square, times F. And the force is the weight of the car on the other side, so that's mg. So that's 1,300 times 9.8 and then plus the density we said is 900, and then G of course is 9.8. The height is 2 meters, and the area is pi times diameter. Area 1 is pi times diameter 1 over 2 squared. Diameter 1 over 2 squared. I pretty much plugged in everything with the exception to the diameters. The pi cancels. And so you can plug in the diameters. So you will get the following. F1 is equal to, by the way, diameter 1 over 2 squared over diameter 2 over 2 squared. The 2's cancel, and we can just put them both under the same, like we just square them both. And since both are in centimeters, I will not convert here. I will just put diameter 1 over diameter 2, that's 6 to 25. Right? We could have converted 0.06 over 0.25, but you would get the same thing. And then times 1300 times 9.8, and then plus 900, 9.8 times 2 times pi. And then here I have to change, because I don't have diameter over diameter. I have to change it to 2 centimeters. Diameter 1 is 6 centimeters divided by 2, that's 3 centimeters, so that's 0.03 meters, and you square it. And this gives us a force of, let me just check the answer. You get 782 newtons. 782 newtons, all right? So the next thing I want to do, the next topic is buoyancy. Or Archimedes Principle. So, and then it discusses floating and so on. So if you put an object inside the fluid, how much force does it experience? Okay, well, let's see. I need to write down the topic. Get my other pen. So we have all been in a bath of water or a pool or something, and you feel lighter. You feel as if somebody is trying to push you out. And there is. And we can understand it in the following manner. So imagine you have a tank of fluid, right? Tank of fluid here. And we would like to know, first of all, the tank of fluid is at rest. It's in equilibrium. Whatever the fluid is, it's in equilibrium. So take an imaginary piece of that fluid, whatever arbitrary shape you have. Let's say it looks like this, right? That's the shape. So I just look at that spot in the fluid and I just isolate it mentally, like in my mind, like virtually, like this. And I say, well, it's not moving. If it's not moving, I know gravity is pulling it down, whatever it is. Gravity is pulling it down, mg. Now, why is it not moving, this piece of fluid? Why isn't it sinking into the fluid? Because, well, if it's at rest, there has to be a force that balances this, and it's going upward. That force called the buoyant force. And the buoyant force will equal to the weight contained in this volume of fluid. So this buoyant force, Fb, will equal to the weight of the fluid. The weight of the fluid within this shape here, whatever it is. Now imagine I carve out that shape and I bring a different material now and I stuck it inside. Okay, so here is what I'm going to do. So imagine this. I take a potato and just sink it in, or put it inside. So let's say that now it's an actual, not just a virtual thing. It is an actual thing. It's a piece of potato or metal. So let me just put it here. Whatever that shape is. Now gravity still exists. G. This was the mass of the fluid. Now I have replaced it by this object here. So this is the mass of the object. Whatever the object is, that's the mass of that object. It will experience a force upward because the fluid does not know whether what's next to it is water, is the fluid like it, or it's the object like, or the object. So it is ready to support, if you replace this by fluid exactly like it, by this what used to be fluid here, the fluid is ready to support that amount of fluid and provide you with a force upward equal to the weight of the fluid that used to be contained in here. This is the buoyant force. So whether this object sinks or floats, it depends. If the buoyant force is equal to the mass times gravity of that fluid, then it will float. If the buoyant force happens to be less, then it will sink. And so that's what happens. But the buoyant force is simply equal to the weight of the fluid that is displaced, and that's called Archimedes' principle. And again, it's an application of Newton's law. Again, the reason we use these names, Archimedes, Pascal, and then later Bernoulli, we use the names, especially Archimedes and Pascal, is because they were discovered before Newton, and Archimedes especially lived ancient. And so we just give it the names of these, but they're all consequences of Newton's laws. The same thing with Kepler's laws, if you remember from the previous chapter with planetary motion. We still call them Kepler's laws because they were discovered by Kepler, but they're really an application of Newton's second law and universal law of gravitation. All right? Okay, so that is the buoyancy, and there are applications to that. So for instance, let's say I take a piece of wood and I want to, let me see, I have 8 minutes. So let's say I take a cube of wood, 10 by 10 by 10 centimeters, block of wood, and it's 700 kilograms per cubic meter, the density. So here is a piece of wood. First of all, here is the fluid. Right, here is the fluid. Here is the piece of wood. It is 10 centimeters by 10 centimeters by 10 centimeters. As you would imagine, the wood wants to float, right? It's a cube of wood, right? It looks like this. It wants to float. Now, how much force do I have to apply to keep it sinking? So I have to push it this way. I have to push this way with a force F. Push. To keep it in here. So let's say it's floating. What are the forces on the piece of wood? Well, there is mg, the weight of the wood itself, mass times gravity, and then there is the buoyant force because it's in the fluid. It's in the fluid. And let's say the density of the wood is 700 kilograms per cubic meter. The density of the water is 1,000 kilograms per cubic meter. And we would find out soon that if the density of the material is less than that of the fluid, it will float. If it's higher, it will sink. If it's exactly equal to it, it will just blend with the material. Wherever you put it, it will just stay there. So I have two forces down and one up. So I get the buoyant force, that's upward, minus the F push, that's downward, minus mg. And I want to just hold it there with the push so it doesn't move, so they are equal to 0. The net force on this object equals to 0. And so the buoyant force, I'm looking for the push, how much force I push with. So F push will equal to the buoyant force minus the weight of this object, of the piece of wood. So first, let's figure out what's the buoyant force. The buoyant force will equal to the weight of the fluid displaced. How much fluid, first of all, displaced? So let me write it in words first. Weight of fluid displaced. And this is the weight of the wood, of the submerged object. The weight of the fluid displaced, the weight of anything will be the mass of the fluid displaced times gravity. And the weight of our piece of wood is the mass of the wood times gravity. Okay, we're not given the mass of the wood, but we're given the volume of the wood, so we could calculate the mass of the wood. Now, the mass of the fluid, how much fluid, what's the mass? Well, it's the density of the fluid times the volume of that fluid. That's the mass of the fluid times gravity. And then minus, what's the mass of the wood? Well, it would be the density of the wood times the volume of the piece of wood that you have submerged times gravity. Okay, so here, the volume of the fluid displaced and the volume of the piece of wood, they will be equal because you completely submerged it. So this volume that used to be occupied by the fluid is now occupied by the piece of wood. Therefore, the volume of the piece of wood has displaced an equal amount to its volume of fluid. So the volume of the fluid will be the volume of the piece of wood. So VF and VW will be the same. I'll just call them V. And G is common also. So I will just have the density of the fluid minus the density of the water, of the wood. W stands for wood, not water. This is the fluid. I should have used wood. All right, so W for wood. Okay. And then the volume and gravity. And now, this is the push. F push. F push. F push. F push. F push. Notice if the density of the wood is larger, the density of this object, if the fluid is more dense than the object, then this number will be positive, and the push will have a positive magnitude. The direction is downward. So it will be as we expected. However, if this density is larger, then we will have a negative sign, so the push will be in an opposite direction to what we expected. And so we actually don't even need to push it. It will float anyways. So as you can see, if the density of the fluid is higher, it will sink. You need to push it to force it to submerge. If it's lower, then the force will be the opposite way, and you actually have to hold it from the bottom for it not to float. So already you can see. Okay, the density of the fluid, well, we have water here. Density of the wood is 700. The volume is 10 by 10 by 10. That's 0.1 meters by 0.1 meters by 0.1 meters. That's over 1,000. 0.1 times 0.1 times 0.1 is 1 over 1,000. And then G is 9.8, and we have what? 300. 1,000 minus 700 is 300, and 300 divided by 1,000 is 0.3. 0.3 times 9.8, and I think that's 2.94 newtons. 2.94 newtons. But let me double check it. Yes, it is 2.94 newtons. Okay. And so this problem is a good problem, I think, because we have come to the conclusion that, well, we did an example, and then we came to the conclusion that if an object is denser than water, it will sink. Not water. When I say water, I really mean fluid. And if the object is less dense than the fluid, it will simply float. Okay? We will do one more example before we move to fluids moving, fluid dynamics. I will see you in the next video.